So it's my pleasure now to introduce our session 2 plenary speaker, Lisa Goddard. She's director of Columbia University International Research Institute for Climate and Society. She's leading the Institute research efforts on understanding and predicting climate change on the 10-20 year horizon. She's also an adjunct associate professor in Columbia's Department of Earth and Environmental Sciences. She's a globally recognized expert of El Niño and La Niña decadal prediction and near-term climate change. She recently served 2 terms on the Board of Atmospheric Science and Climate of the U.S. National Academy of Science, and she's been chairing U.S. CLIVER and co-chair the International CLIVER Panel, which advises and coordinates international research on climate and the ocean under the WCAP, which is the World Climate Research Program. In 2007, she developed PACE, which is a national postdoctoral program that explicitly links climate PhDs with decision-making institutions. And she will be presenting on 10 years out, navigating the information gap between El Niño and climate change. But we need to switch computer because she's using her computer, so hold on a second.
Mac people.
We're a special breed. Okay, bring it up.
Okay. Yep. Okay, thank you very much. So thanks very much to the organizers for inviting me to this meeting and for all of you for showing up for the plenary session. As my talk title suggests, I'm going to be talking about decadal variability and prediction. This is really a frontier area for diagnostics and prediction in the climate community. And it's not just about, this is another time scale in the climate system, but understanding those timescales and what we know about El Niño and climate change, how that can help us better understand what we're facing with decadal variability. So just to get us all on the same page with these timescales that I'm going to be referring to, I wanted to start with this timescales decomposition. So what you're seeing in the top graph on the slide, in the black line, is globally average temperature over the 20th century. So this is from observations over land to the extent that we actually have that data. Annual mean temperature year by year through the 20th century. And so we can decompose that into its different time scales, not necessarily in an attribution sense, but just to get an appreciation of the relative importance. So in the top graph with that red line, what we've done is to regress a climate change index that tries to capture the timing of the planet's response to changes in radiative forcing. So that includes changes in greenhouse gases as well as aerosols, volcanoes, and natural drivers of that as well. So that's the trend. We can take the trend out of the time series and we're left with approximately natural variability, which we can then low-pass filter, high-pass filter. So we can remove or identify timescales that are 10 years or longer. That's the green line that I'm calling decadal variability, and everything on shorter timescales then is the interannual variability. And that's where El Niño sits, for example. So you can see that even on this globally averaged scale, we have about 1/5 of the variance that was observed in the 20th century is in that interannual variability. We know that El Niño and La Niña events have an impact on global temperatures. That 13% variance in the decadal may not seem very big. Certainly at the global scale, trend has dominated the temperature that's been observed. Once you get to smaller scales, the variability becomes a more important thing. But once you start to look at this combination of decadal variability and trend, you start to get some pretty interesting insights, and in part because the human psychology is pretty short time frame. So it's very easy to convolve what we're seeing in the total climate system with just climate change, and in particular for certain aspects of the climate system that have short records. But if you look at the decadal variability and the change together, which I've now put on that one graph on the right, you can see that there are some interesting periods that stand out, in particular from what the media has portrayed, even what the climate community has talked about. So in the 1980s, when the decadal variability is leading to warmer conditions on top of the climate change, there was a lot of discussion about climate change acceleration. Climate change is accelerating, it's getting bigger, how much more is it going to accelerate? But then that decadal variability turns around and it goes through a phase of relative cooling. Climate change keeps on, but that intersection that's now offsetting the climate change trend has been termed the hiatus, maybe a plateau in global warming. But we can see that man-made climate change is not slowing down or taking a hiatus. It continues Al Gore off the top of this graph, but it's the fact that we're experiencing all of these things together. So that's the time scales. Now, how do we start to understand those in the sense of decadal variability and its prediction? So starting again with El Nino, this is a picture from the 2015-2016 big event. El Nino is an oceanic phenomenon, coupled ocean atmosphere. The time scale of El Nino is largely set by oceanic processes and that coupling as well. And certainly the memory, the ability to predict is very much dependent on ocean state and its evolution. It's important to measure that. Again, this is a very big El Nino. One of the biggest on record. Some people called it the Godzilla El Nino event. What was important about that, though, these big events really get people's attention. And so because of these big events and the one preceding it in 97, 98, it brings greater public awareness to El Nino itself and the regional climate impacts that it has around the world. Now, on the other side, climate change, and I'm using I know, very old slide, but I like it for its simplicity. So we're very aware of the fact that increasing greenhouse gases is driving globally average temperatures up, and that carries with it an expectation for a pattern of temperature changes and precipitation changes. Ocean plays a role in that as well. But so here we have the driver being that external forcing to the natural climate system, that increased radiative forcing due to our changes in the atmospheric composition. Now, decadal variability and its prediction sits somewhere in between that. So it's not just that the time scale is in between, which it is, but we know that the slow changes in the ocean circulation and resulting sea surface temperature patterns is influenced by those initial conditions. The initial ocean state is very important to how we understand and how we simulate decadal variability. At the same time, when you're looking out 5, 10, 20 years in the future, the changes in radiative forcing is going to build up in the system, and that will be part of the climate that you experience on those time horizons. So up until quite recently, folks thought, well, you know, the decisions that I need to make, or at least the time scale at which the decisions I make are going to be evaluated, are fairly short, 5 years, 10 years out. And so the climate change projections that I see in the IPCC are all talking about the end of the 21st century. But those models are going through the whole period between now and then, so I'll just use the next 10 or 20 years of data, and that'll tell me how climate change is going to affect my system. The problem is decadal variability. So if you look at these even fairly large regions, subcontinental scale regions, you will see decadal variability in the climate system. What the graphs are showing you on the right, the black line is from observations, the colored lines, some handful of models. We've taken out the year-to-year variability, so you're just looking at this decadal and trend components of it. You absolutely see these decadal fluctuations in the observations, and you see it in the models as well. The models have decadal variability, but those models are effectively free-running other than the radiative forcing that we're imposing. So there's no reason to expect that the decadal fluctuations in those climate change projections should be synced in time with the observations, because that initial conditions, the ocean state is not coming into those projections as the projections proceed. So we need to consider both of those things. So through the rest of my time, what I'd like to do is just to give you, just go through the phenomenon that's responsible for decadal variability. There are processes in both the Atlantic Ocean and the Pacific Ocean that are driving this. So I'll just describe how it is that we identify and monitor these phenomena, what sort of regional climate effects that they have, and why we have some inkling that we might be able to predict these. I'll give a little overview of experimental decadal predictions so far, and if there's time, I will show you a quick example at the end. So starting with the Atlantic multidecadal oscillation, or Atlantic multidecadal variability. So the Atlantic meridional overturning circulation is very much at the center of what we understand about decadal variability in the Atlantic, as well as our attempts to predict it. So what you're seeing in this map here, the red arrows are showing surface currents, the blue arrows are showing you the deep currents returning southward, and then you see where the storm track is, the ITCZ, for example. So the AMO is typically indexed as the average temperature over the North Atlantic, and that time series smoothed is shown to the right. And so some very obvious features that come out of that time series, you see these multi-decadal shifts. They can be quite long in their duration, but you also see a trend. Now we know that when the North Atlantic warms up, that has impacts on the regional climate. It influences the Atlantic hurricane season. In fact, this actually was the realization that drove identifying the AMO in the first place, was the fact that we had decades with more active hurricanes and decades with less active hurricane activity. And so we know that has an influence. It's also been linked to drought over the United States. It influences rainfall over the Sahel and even as far away as India. So there are global impacts related to the AMO. Typically, though, in the index, we remove the trend. And so we're looking at a detrended measure of North Atlantic temperatures. And so this is what you'll see going forward. The instrumental record is quite short, as you even get a sense from this graph here. So at the top, that's the instrumental record, but using proxy data, that index has been pushed back thousands of years. So we know that the Atlantic has had these increases and decreases in the strength of the meridional overturning circulation, which then has an influence on the sea surface temperatures across the North Atlantic. That's been going on for thousands of years. The periodicity is not strong, but it's a long time scale phenomenon. The fact that it's tied to the Atlantic meridional overturning circulation and that the models somewhat capture that gives us hope that there may be some prediction. And here's how this thinking goes. So if you have the time series, which is the upper left, if you have a time series of the AMO, and you know that that's related to the overturning circulation, if we just regress that time series on sea surface temperatures worldwide, the pattern that we get is just below the time series. So that's from observations, observed sea surface temperatures. You can see the clear signature of warm temperatures across the North Atlantic. There's some imprint of that regression in other parts of the ocean, but focusing on the North Atlantic. Now, what the Met Office scientists did was to look at their model and what do the sea surface temperatures look like when their overturning circulation speeds up or slows down. So they took an index of the overturning circulation strength and regressed that against sea surface temperatures in their models, and what they got out was a pattern that looks very similar to what we observe. So in their case, they've tied it directly to that overturning circulation. We don't have the data to do that in the observed world. But the fact that it looks very similar to what we see related to the AMO is encouraging, because now we do have something physically to tie that pattern of sea surface temperatures to. And we know that if we capture that pattern of sea surface temperatures, the changes in heat flux into the atmosphere will then result in the types of expected climate impacts that have been associated with the AMO. So the idea is predict the overturning circulation. That relates to a fairly realistic sea surface temperature pattern, which then can be used to drive predictions. So that's where the hope sits with the Atlantic. Now going to the Pacific decadal oscillation was originally identified as a pattern. And there have been a few attempts to define that index, that they all regress fairly much to the same type of pattern and the same type of variability. So I'm going to go with the one that was initiated by Nate Mantua in our audience here. So what's shown at the top left map is the sort of canonical positive phase of the PDO. The colors are showing temperature, there's contours for sea level pressure, and then the arrows are the low level winds. So just focusing on the temperature pattern, you can see that there's this warmer than average condition in the equatorial Pacific, cooler conditions in the mid-latitude Pacific, and the negative PDO phase, which is on the other map, is showing fairly the opposite. The time series then is effectively regressing the observed sea surface temperatures at some point in time on these canonical phase maps. So to the extent that the observations looks like the positive phase of the PDO, you will get a red bar going up. The more it looks like that pattern and the stronger that sea surface temperature anomaly is, the bigger the red bar will be, and oppositely for the negative phase. And so you see these multi-decade long epochs where the PDO is predominantly in a positive phase or predominantly in a negative phase, but there's also a lot of variability in that time series, a lot of variability from year to year, and it makes it very difficult even to predict where you are now, where are you in the PDO. As you can see in the about the 1960s, it looks like it's coming out of that cold phase and it drops right back in again. So it's very hard to nowcast the PDO or the change in phase of the PDO until you've been in it for a while. And that's one of the complicating factors. So we know that there's similarities between the PDO and ENSO. This is just regressing those time series of the decadal variability on sea surface temperatures and then the interannual variability on the sea surface temperatures. The pattern's quite similar. The interannual variability has a stronger signature in the tropics. The decadal has a stronger signature in the mid-latitudes. And in part, that's the processes. But the fact that there is this tropical signature and there's a symmetry in the response in the mid-latitudes suggests that there's a tropical driving. And that happens through the atmospheric bridge. The idea here is that tropical heating influences atmospheric circulation that can change the sea surface temperatures remotely. So that was described in the 1970s, this process of tropical heating, and then later related by Mike Alexander to the processes associated with the PDO. So here you see in this gray area representation of tropical heating that generates atmospheric Rossby waves. You see this wave train propagating out of the tropics, and that high pressure, low pressure is enhancing the westerlies as coming across the Pacific. You get Ekman transport that then moves the colder high latitude water into the mid latitude. So that's a dominant term in the sea surface temperature changes for the mid latitudes. But interestingly, it's not these physical atmospheric processes that really identified the PDO in the first place. It was the fish. It was the marine ecosystems. So this is a fairly short time series on the right. What's shown on the right is the different types of species being caught off the coast of North America. And you can see the change over time where it's consistent. That's starting in about the 1970s, going through the 1990s. And so seeing in the 1970s, very dominated by shrimp, going to larger species in the 1980s and 1990s. And if you had only this data to look at, you might assume that that's a trend. Maybe this is climate change. But we recognize that these things have been going on for some time. And so the analysis of the marine ecosystems, these biological indices, has this variability where you see this shift in the 1970s from this negative phase to a positive phase of the PDO. And that physical indices is looking at the climate measures that we were talking about before, sea level pressure, winds, sea surface temperatures, and we see those physical indices changing in time consistently with the biological indices, although maybe slightly noisier. So being able to say something to understand the decadal variability in the Pacific and maybe even predict it would give some hope to predicting these types of ecological shifts. So just quickly on experimental decadal prediction. So starting from our climate change projections, what we want to know, since we're looking out at a time scale, we know that the radiative forcing is going to be important. Can we add value and capture that variability if we bring in that initialization of the ocean state? So how do we treat radiative forcing? That's a question as well. And it was realized that, well, if we're only looking out 10 or 20 years, the differences between those different emission scenarios are not that big, even on certainly on the globally average scale, but even if you look on the maps, these are 3 different scenarios for a 20-year climatology, the next 20 years. And those maps are almost indistinguishable from each other. So the idea was that you don't really need to know the details of the emissions as long as it's increasing in some realistic sense. But you do need to initialize the ocean, and here's where the Argo floats become absolutely critical. But these only started to be deployed in the beginning of the 21st century, so we have a very limited amount of data to work with. This is a fairly recent map of where those Argo floats are, close to 4,000 floats. It's been fairly constant for the last few years, but those floats have a lifetime. They have to be replaced every 4 or 5 years. So this is an ongoing effort. If there's a genuine interest in predicting decadal variability, this observational network is absolutely critical to making that happen. Now, it looks like it's well observed, but these dots are about the size of Los Angeles, and the floats are not bigger than me. So, but it's still incredibly well sampled, and it's temperature and salinity measurements that we just did not have, really important for the initialization. So how is that helping? The short answer is, so far it's not a lot. But I think that there's a lot of room to improve on that. Let me start with the middle graph, the middle set of graphs. On the left-hand column, you're looking at mean squared skill score. That's a measure of accuracy. And on the right, you're looking at correlation. So the correlation, you want things to go up and down at the same time. Now, in the middle graph, those are the skill maps from the decadal predictions. And usually when you hear talk from a center that's doing decadal predictions, that is all that they will show you because they look brilliant. They look absolutely fantastic. Now, as a skill score, you have to measure it against something, and the something that you're measuring it against is assuming that nothing's going to change. So, of course, things are changing. You're going to do better by having some decadal prediction that's got radiative warming. On the right, the correlation looks great because it's capturing the trend. You've got 1 degree of freedom. Everything's getting warmer. Correlation looks high. On the bottom, which looks very similar to the middle, the bottom are the uninitialized projections. Same models. These are the climate change projections you would get from IPCC. Same models in the middle, but now initialized with the ocean state. So the top, now you can look at the top, is showing the difference between those two. And if you look at the correlation where the map is practically blank, that's indicating that we are actually not capturing that up and down that we're hoping to capture yet. But on the left, you do see positive improvements in skill, and that again is because of the initialization. We are, by initializing the ocean, bringing the state closer to the observation so that 10 years out it's still going to be closer to the observations. So even if we're not capturing the fluctuations yet, we're still improving the predictions on the trend, and that's a useful contribution, and there have been incremental improvements forward in that. So I, in fact, don't have time for my example, but I'm happy to talk to folks afterwards. So I'm going to just skip to my summary slides. I believe it's really important to consider the commingling of decadal variability and climate change, in particular because so many of the indices and measures that we're looking at these days are pretty short. Satellite data, health data, a lot of the biological measurements. But both the Pacific and the Atlantic are involved. In some cases, for example, US drought, both of those things can act together. But both of those types of variability impact regional climate and the ecosystems on land and over ocean. We're trying to predict those to provide not only better understanding of what actually did drive that variability, but also to provide some hopefully better preparedness and planning for the risks that these things can pose. Now, decadal predictions are still incredibly new, but there is some indication that the initialization of the oceans is adding value, and as we start to bring in the methodologies that are used in both seasonal prediction in El Nino and climate change projections to take the most from the models and what they can provide, I think that we're going to see more advances in the very near future. But this is an extremely active area of research right now in the climate community. So thank you.
Thank you, Lisa. I think we have gaps between social scientists and natural scientists, but we also have gap between internal and decadal predictability. So this is time for question. We have time for a couple of questions. Shinichi, please.
Yeah, thank you, Lisa, for your very nice talk. And always I'm disappointed about the Pacific decadal prediction. So what is the main cause to decrease the scale of the Pacific? What is your idea?
What's needed to improve the skill? That's a really tough question. I think I'd have some really big grants in my pocket if I had the answer to that. Initialization is still an issue. I think in the Pacific, although we have an excellent array of monitoring in the tropical Pacific, we don't have that same level of sophisticated monitoring in the mid-latitudes, even though we do have the Argo floats. So the processes by which the mid-latitudes hang on to the temperature anomalies that are driven by the tropics, I think is a very difficult thing for the models to capture. I also believe that there's just many processes going on. I've only talked about one linkage, which I think most researchers on the PDO would indicate as the dominant, and that's the driving from the tropics. But there's also implication of Rossby waves shedding off from the Kuroshio that can transport across and influence the gyre circulation. So there's a few processes going on. Not all of the models get that, so they may be getting part of the response, but not the whole response. So I think there's a lot to understand the processes as well as the model's ability to capture that and then moving into the prediction. But it's very complicated, and in part because the interannual variability is so dominant in the Pacific.
Thank you very much.
Please, Jack.
Thank you, Lisa. Can you relate the PDO and NAO to the atmospheric variability, the various oscillations in the Arctic? And then just second comment, what about the Southern Hemisphere?
Sure. So I'm going to ask you to clarify on the Southern Hemisphere, if you will.
Well, just based on what I said about the oscillations in the greater Northern Hemisphere jet stream and how those are related to the two basins. Same comment about the Southern, if there's Southern Ocean atmospheric oscillations on those timescales.
Okay, so I mean, the short answer is that most of these things are interacting with each other. In the Northern Hemisphere, you mentioned the NAO. There's considerable research growing that the NAO is potentially one of the triggers for AMO to change sign. sort of like a warm water buildup before an El Nino event that then requires westerly wind burst triggers. So if you may have the overturning circulation, the state of the Atlantic poised to change phase, and it takes that trigger from the NAO to actually allow it to change phase. That's one thing that links them. In the southern hemisphere, I'm not aware of the same sort of linkages between, say, the southern annular mode and this variability. What you do see in that PDO map, you have that symmetry. So, and in fact, the Australians will refer to the interdecadal Pacific oscillation so that it captures the whole Pacific basin. You have that symmetry. The fact that it's weaker in the southern hemisphere mid-latitude is quite likely due to the seasonality. The fact that El Nino events, El La Nina events peak near the end of the year, which is the southern hemisphere summer, so those high pressure systems are going to be weaker, means that the Rossby wave response on that southern hemisphere jet stream is going to have a weaker influence on the oceans there.
Yeah, thank you. I wanted to ask a question generally about Kalman filtering. So in an attempt to kind of relate this to how fisheries models have proceeded, I think we have both kind of process and sort of statistical state space methods that we use. And obviously the topic of initialization is sort of related to Kalman filtering, and my understanding is weather models also sometimes do ensemble Kalman filters on top of the process. And so I guess, do you have anything to say about that?
So I am not in the data assimilation world. I recognize that it's one of the three legs of the chair that we need to do prediction. I also know that the pioneering work that Doug Smith did at the Met Office was incredibly innovative and creative in the way that he took such a limited amount of salinity data and was able to sort of iteratively assimilate that into a system, because those decadal prediction experiments started in 1960. We had practically no salinity data. So assimilation creativity has been a really important part of decadal prediction.
Actually, I have a question. You've listened to Andrea's talk talking about how difficult is it to model oxygen because of global and local processes and various scales of variability. So you showed the Argo floats, which is about 4,000 floats. But if we think about BioArgo with oxygen sensor, we're left like with a few hundreds. So do you think the future of our prediction relies in these BioArgo floats with more sensors being equipped on it?
It's a shout out for the program managers. Yes. I think the more data that we can get on the oceans, the better, because all of these things are related, and there's so much that we don't know. And having a limited amount of data, it's very easy, given the long time scales in the ocean, to draw the wrong conclusions. So I don't have any direct working with oxygen data myself. I know, working with the temperature data, that the ocean models, and this was pointed out by Andreas, the ocean models have difficulty in capturing some of these important features and characteristics of the upper ocean. But I think the only way to really improve those processes and identify how important they are to our ecosystem, which we all depend on, is by having that data.
Shinichi,
one more.
last question?
Yeah, one more question. So regarding on the ocean process, I think the mixing is one of the most big gap for the knowledge. And mixing is also controlled by the tide. And the tide has 18.6 years, very long oscillations. So is there anybody try to include the 80.6 years tidal oscillation for decadal prediction?
Not that I'm aware of. Thank you.
Okay, thank you, Lisa. Let's give a big applaud. Yes.